So let's go ahead and take a look at the first example. The first thing to note when we do limits is we always try what I call inspection. Okay, what I mean by inspection is let's just inspect the form of the limit. Basically like a direct sub, okay? I don't say direct sub all the time though. Inspection is more of a generalization and you'll see why later, but for now let's just try direct sub and just call that inspection instead. And again, I'll explain why later I call it inspection. So let's go ahead and try direct sub. If I try that, I get 2 minus 2 on top, which is 0. On the bottom, I get negative 1 plus 1, which is also 0. So inspection gives 0 over 0. And if I have 0 over 0, that's an indeterminate form, right? It doesn't mean that the limit doesn't exist. It doesn't mean the limit's 1. It doesn't mean the limit's 0. It doesn't mean the limit's infinity or negative infinity. All it means when we have 0 over 0, or an indeterminate form, is that we cannot determine what the limit is as is. We need to find another method to use. That's what an indeterminate form is. Okay, we just cannot determine what the limit is right away. So we learned in chapter 2 that we could do factor and cancel, so you could do that here. Try that on your own as an exercise, but here we're going to try something else called L'Hopital, right? And L'Hopital, we know that we're going to take the derivative of the top divided by the derivative of the bottom, which you should have learned already, so we'll just do this one a little bit quicker. And again, the point of that is to compare the slopes, the ratio of the slopes, right, of the top and bottom. What I'm going to do here is take the derivative of the top divided by the derivative of the bottom. So really what I'm doing is looking at the ratio of the slopes. So I have 4x over 1. Every time you do L'Hopital, please indicate so, otherwise it'll be too difficult to follow your work. So you could just put an L or an H or an LH over the equal sign, indicating that we're doing L'Hopital. Now let's go ahead and try inspection again, or direct sub. So if I plug the negative 1 in, am I going to get a real finite number? Yes, I'm not going to get an indeterminate form, so I could go ahead and plug in the negative 1. I have 4 times negative 1, and so that's negative 4. And that was a basic L'Hopital problem. Okay, so now we're going to see some others. So now let's try inspection on the next example. Here, if I try direct sub, I get e to the 0, which is 1, minus 0 minus 1. So again, I have 0 on top, and the bottom, if I plug in x equals 0, I also have 0. So again, I have 0 over 0, which is an indeterminate form. If I have 0 over 0, I could go ahead and apply L'Hopital. So let's go ahead and try that. Again, indicating that I'm going to do L'Hopital by writing an LH over the equal sign. So now I take the derivative of the numerator. So don't forget about chain rule. We have 2 e to the 2x minus 2. And then the bottom, the derivative is pi times 2x, right? Because pi is just a constant. So if we did 5x squared, if we found the derivative of 5x squared, it would be 5 times 2 times x. So here we have pi times 2x. The limit signs are important here because if I didn't have the limit signs, then these two functions are not equal, so the statement is now false. So anytime you're working with limits, especially L'Hopital, if you're going to apply L'Hopital, you need those limit signs there. Otherwise, you're demonstrating that you don't really understand the material because it's not the functions that are equal, it's a limit of those functions that are equal. So now if I try direct sub, okay, I get 0 over 0. So if I get 0 over 0, well, it doesn't mean I did anything wrong. It just means we still have an indeterminate form. So if I have 0 over 0, I could go ahead and apply L'Hopital again. Applying L'Hopital again, the derivative of the numerator by chain rule is 4 e to the 2x. The bottom, 2 pi times x, so the derivative is just 2 pi. Now we go ahead and try direct sub again. I plug in x equals 0. I go ahead and try direct sub. I plug in x equals 0, I get 4 e to the 0 over 2 pi. E to the 0 is 1, so I'm just left to reduce to 2 over pi. Next example will show us why I call this inspection instead of direct sub. Because if we find the limit as x approaches infinity, we can't call that direct sub because we can never plug infinity into a function. For example, you can't find sine of infinity, or infinity squared, or square root of infinity, or e to the infinity. You cannot plug infinity into a function, right? Because infinity is not an actual number. We cannot evaluate a function at infinity. So that's why we can't do direct sub. We cannot directly plug infinity into some function. We can't ever be at infinity. We can only be near infinity. So that's why we say inspection, we can't be at infinity. So instead of doing direct sub, we just think what happens as we get closer to infinity. So we look at the numerator and we say, okay, well, as x approaches infinity, as x gets larger and larger, then ln of square root of x also gets larger and larger. And the denominator, x to the 1/4, or the fourth root of x, as x gets larger and larger, so does x to the 1/4. So inspection gives infinity over infinity, which is another indeterminate form. Again, infinity over infinity doesn't tell us anything about what the limit is. It just tells us we cannot determine what the limit is right away. Let's go ahead and find another method. Namely, let's go ahead and use L'Hopital. So I notice here that if I'm going to apply L'Hopital, well, I'm going to have to take the derivative of the top and bottom, but it might be easier if I use law of logs to simplify. So law of logs are great for simplifying to make calculations easier. So I'm going to take that ln of square root x, or in other words, ln of x to the 1/2, and bring that exponent out in front. So again, this is ln of x to the 1/2. If I have an exponent, I could bring it to the front. I also just rewrote this so it's easier to calculate the derivative. The fourth root of x can be rewritten as x to the 1/4. Now I'm ready to go ahead and take the derivative of the top and bottom using L'Hopital. Remember, with L'Hopital, we're not applying quotient rule. Okay, so don't be confused about the fact that it's a fraction. We're not applying quotient rule. We're taking the derivative of the top divided by the derivative of the bottom, because what we want to do is we want to compare the slopes. That will tell us that will give us a good idea of what the limit is. So taking the derivative of the top gives 1/2 times 1 over x. The derivative of the bottom is 1/4 x to the negative 3/4. Now, every time you do L'Hopital, always, always, always simplify that function first. Don't keep going. Don't try to do L'Hopital again or anything like that. We always want to simplify the function first, because if you check inspection here, we get 0 over 0, and then you might think to go ahead and do L'Hopital again. But if you do that, you're actually going to be doing L'Hopital forever. So always, always, always simplify that function first before you ever think about doing L'Hopital again. So we're going to simplify this. I have a negative exponent in the denominator, which we don't really like. We don't like double fractions either, right? So let's get rid of that. Let's just simplify this. This is the same thing as 1 over x to the 3/4 in the denominator, so I'm going to flip it and multiply this. My numerator is 1 over 2x. My denominator is 1 over 4x to the 3/4. I'm going to flip it and multiply. I simplify this further. I know that if I divide two exponentials with the same base, I subtract the exponents, right? And I'm just left with x to the 1/4 on the bottom. Now when I find the limit, I know that if I have 2 over some x to the 1/4, where x is getting larger and larger, so if that denominator is getting larger and larger, then I know that this fraction is getting closer and closer to 0. Again, don't plug infinity in. We cannot evaluate x to the 1/4 at infinity. So what you don't want to write is this, because that's incorrect, right? We don't ever want to plug infinity into a function. So don't do that. One of the more important concepts is to always try inspection first. If you go ahead and apply L'Hopital just because you see a fraction, if we don't have an indeterminate form, you are absolutely going to get the wrong answer. So always try inspection first. Okay, if I try inspection here, which I can just do direct sub because I don't have infinities here. So let's just go ahead and directly plug in. Inspection gives e to the 0 over 0 plus 2. E to the 0 is 1, so I just get 1/2. My answer is 1/2 by direct sub. Okay, that's my answer. I don't go ahead and apply L'Hopital. So that's why it's really important to check inspection first. So I abbreviate direct sub as DS. So we just say, okay, well, if I just try inspection, or in this case direct sub, I plug in x equals 0, I get 1/2, so that's my answer. I don't go ahead and do L'Hopital. So let's go ahead and see what happens if we did apply L'Hopital. I take the derivative of the top, which is e to the x. The derivative of the bottom is 1. And now I try direct sub. I get e to the 0, which is 1. We could see here that if we applied L'Hopital without checking inspection first, we would have gotten the wrong answer. So again, L'Hopital you can only use when you have 0 over 0 or infinity over infinity. Anything else you have, you cannot apply L'Hopital. It's not going to work. That's why we always want to try inspection first, otherwise we will get the wrong answer. Always check inspection. If you don't have 0 over 0 or infinity over infinity and you go ahead and do L'Hopital, you're going to get the wrong answer like we did here. This one was just a simple direct subproblem. Let's see what happens with the next one when I try inspection. I get e to the 0 over 0, which is just 1 over 0. Well, 1 over 0 is not an indeterminate form, so we cannot apply L'Hopital here either. In fact, this is just a limit from chapter 2. It's just going back to a review of chapter 2, and we have to go ahead and just find what the limit is without L'Hopital. So I know that if I have 1 over 0, in other words, if I have a non-zero number over a 0, that tells me my limit's going to be infinity or negative infinity. Because if I have something, if my numerator is approaching 1 and my bottom is approaching 0, it's not equal to 0, it's just very, very, very close to 0, so something like this. And I know that this is going to be a very, very large number, because I divide by something really small. So I could approach 0 from the right side, like this one, and I have infinity, but if I happen to approach 0 from the left side, then I'd have a really, really large number, but also negative, right? So maybe close to like negative 1 billion, or close to negative infinity. So if my fraction is approaching 1 over 0, it doesn't mean the limit's undefined. Yes, the value 1 over 0 is undefined, but here we're just saying the numerator is approaching 1, the denominator is approaching 0. So in reality here, if that happens, then the whole fraction is either approaching infinity or negative infinity. So now we just have to determine which. Well, here I'm given that x is approaching 0 from the right, so I just have to look at values slightly larger than 0 and see whether that's positive or negative. Because if I know that 1 over 0 gives me infinity or negative infinity, then what happens is if I'm on the right side of 0 and I plug in something positive, I have to be obviously approaching positive infinity. But if I plug in something to the right of 0 and I have a negative value, then I'm obviously going to be closer to negative infinity. So I call this method plug-in rule, okay, abbreviated as PIR. I just made the name up just to call it something, so I have something to refer to it. But again, it's called plug-in rule. And again, what happens is if I have a non-zero over a 0, then this tells me the limit is either positive or negative infinity. So again, if I have a non-zero over 0 when I try inspection, that tells me the limit's either positive or negative infinity. I just have to determine which. So what I'm going to do is look at values slightly larger than 0, okay, because I'm coming from the right side, and see whether I have positive or negative values. So if I look at e to the x over square root x, and I think about values slightly larger than 0, if I think about values slightly larger than 0, well, the exponential function is always positive no matter what. So that's the exponential function. It's always going to be positive. You should know the graph of the exponential function. So we have positive, and then the denominator, if I'm coming from the right side of the square root function, if I take the square root of 0.0001, I know that's going to be positive as well. So we have a positive value, which tells us our limit must be positive infinity. This is called plug-in rule. The first thing we check is inspection. If I get a non-zero over 0, that tells me the limit's either positive or negative infinity. I just have to determine which. I look at values slightly larger than 0 since I'm approaching 0 from the right side. When I have x is slightly larger than 0, I have a positive number, so that tells me the limit is positive infinity. No L'Hopital here because I didn't have 0 over 0 or infinity over infinity. This is not an indeterminate form. Doing inspection on the next one, okay, I can see here that the numerator is going to approach either the 0 or 1, but the bottom, I have ln 0, which doesn't exist, right? You should also know the graph of the natural log function. ln 0 does not exist, right? 0 is not in the domain of the natural log function. So when we say ln 0, don't confuse that and think the limit is undefined or doesn't exist, right? All it means is the function doesn't actually exist at 0, but it doesn't mean the limit doesn't exist, right? Because we're just seeing what happens as we get closer to 0. We're not seeing we're not saying what happens when we're at 0. So I say, okay, well, what happens to the natural log function as x gets closer and closer to 0 from the right side? Again, this is why it's important to know the graph of the natural log function, and we can see here that the y value or the function is approaching negative infinity. Inspection gives 1 over negative infinity. If the denominator gets closer and closer to negative infinity, I have something like 1 over negative 1 billion, which gets closer and closer to 0. There's not much to do here. Again, we don't do L'Hopital because we don't have an indeterminate form. We just see that the top is approaching 1, the bottom is approaching negative infinity, so by inspection, the limit is just 0. Let's try inspection on the next one. Remember, I don't want to actually plug infinity in, so I don't want to say 5 to the negative infinity. So I should never see this, right? We don't plug infinity into a function. We just look at what it's approaching. So what happens to 5 to the negative x as x approaches infinity? Well, 5 to the negative x, we could think of as 1 over 5 to the x. And as x gets larger and larger, so does that denominator. So this approaches 0. So this approaches 0, and then square root x as x gets larger and larger approaches infinity. So inspection gives 0 times infinity. This doesn't mean the limit's 0, it doesn't mean the limit's infinity, it doesn't mean the limit's 1. All it means is that we have another indeterminate form. Whether it's 0 times infinity or whether it's 0 times negative infinity, both of those are indeterminate forms. It means we cannot determine what the limit is from there. So if you automatically say that the limit's 0 or infinity or negative infinity, it's wrong because we cannot assume that, right? We don't know which one's growing stronger. If we have 0 and then we have infinity, they're on opposite sides of the spectrum, so which way is it pulling if we're multiplying them together? We want to find out which one's stronger, or is it somewhere in the middle? So we need to find the limit of this using L'Hopital, but we cannot apply L'Hopital yet because, as I said before, we can only apply L'Hopital when we either have 0 over 0 or infinity over infinity. If we have another indeterminate form besides those two, we have to manipulate the function to get to either 0 over 0 or infinity over infinity. So I have to manipulate this function to get to a fraction form, otherwise I cannot apply L'Hopital. To get this to be 0 over 0 or infinity over infinity, I want to move something to the denominator because right now I don't have a fraction and I need it to be a fraction to do L'Hopital. So I'm going to move something to the denominator, and the easiest thing to move is the 5 to the negative x because it already has a negative exponent, so might as well just move it to the denominator. So I'm going to have square root x over 5 to the x. Now when I try inspection, I get infinity over infinity as x approaches infinity. Now I can go ahead and apply L'Hopital. I take the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. I take the derivative of the denominator. The derivative of a general exponential function is the exponential function itself times the natural log of the base. So the original exponential function times the natural log of the base. And again, before we do anything else, we simplify. If we have negative exponents, if we have double fractions, you always want to simplify that first before attempting to do L'Hopital or anything else again. So let's go ahead and simplify this. So what I could do here is I could just move the 2 to the denominator, I could move the x to the negative 1/2 to the denominator and negate that exponent to become positive 1/2. And now I can try inspection. I know that x to the 1/2 and 5x, they both approach infinity as x approaches infinity. So basically the whole denominator is getting larger and larger as x gets larger. And if the whole denominator is getting larger and larger and the top is staying constant at 1, so say something like 1 over 1 million, then I know that's going to get smaller and smaller, approach 0. So here the limit is 0. So again, 0 times infinity doesn't necessarily mean the limit's going to be 0. Here it happened to be 0, but on a quiz or test, if you had said 0 times infinity, so that gives us 0, well, we can't assume that right away, so that wouldn't really give you much credit, right? So if I have 0 times infinity, that's an indeterminate form. We have to keep going, manipulate it to either be 0 over 0 or infinity over infinity so that I could do L'Hopital. And maybe the answer will be 0. Maybe the answer will be infinity. Or maybe it'll be somewhere in between. But we have to actually do L'Hopital to prove that. If I try inspection here, 3 over x squared approaches 0 as x gets larger and larger, so I have 1 plus 0 on the inside, so the base is just approaching 1. The exponent approaches infinity as x gets larger and larger. So I have inspection gives 1 to the infinity, which is not equal to 1. This is a very common error. It's not equal to 1. 1 to infinity is another indeterminate form, so that means we cannot determine the limit as is. So again, if you have 1 to the infinity, don't write that it equals 1, because it may equal 1 or it may completely equal something else. So we have to use L'Hopital, but we can't use it yet, right? We just know that we're going to have to use L'Hopital eventually. So again, we can only use L'Hopital if we have 0 over 0 or infinity, meaning we have to have a fraction. And right now, not only do we not have a fraction, but we have an exponent that we need to get rid of. So I need to get rid of that exponent somehow. So what I'm going to do is use law of logs to get rid of that exponent, to pull it down. Right? So the first thing that I want to do is define this limit. So I'm going to say, let y equal this. And once I do that, now I could take the natural log of each side. I couldn't do that before because I didn't have anything on the left side. So it's important to define that limit, let y equal, and then we have that limit. So now we can take the natural log of each side. So I go ahead and take the natural log of each side. Now I could use law of logs to bring this exponent down to the front. Great, so I don't have an exponent anymore, but now if I try inspection, I have infinity, and then this here, this approaches 0, so I have ln of 1, which is 0, so I have infinity times 0. Infinity times 0, again, is not 0 or infinity, it's another indeterminate form, so that's good, because anytime I have an indeterminate form and I manipulate the function, I should still have an indeterminate form. Okay, so if you manipulate a function, if you move stuff around, and you had an indeterminate form before, now you don't, you probably made an error somewhere, so go back and check your work. So again, we had an indeterminate form, we manipulated the function, we still have an indeterminate form, we're getting closer to the fact that it must be a fraction. Right now it's a product, so we got rid of the exponent, now we have to make it be a fraction, so we have to move something to the denominator. Well, we want to eventually do L'Hopital and take the derivative of the top and bottom, so when we move something to the denominator, we want to think what's easier to take the derivative of if I have to move it to the denominator, and so probably 5x squared versus the natural log. So if I move it to the denominator, I have to put it in a fraction, right? I can't just move the 5x squared down to the denominator. I have to do it like this so that when I actually simplify it, I flip this and multiply and get back to here. Now if I try inspection, I get ln of 1, which is 0. This approaches 0, so now I have 0 over 0. Now I'm ready to go ahead and apply L'Hopital. Indicating when we do L'Hopital, so I'm going to do L'Hopital right now. I'm going to take the derivative of the top divided by the derivative of the bottom. So I'm going to do L'Hopital. I take the derivative of the top, so the derivative of the natural log function is the derivative of the inside over the inside. And then I'm going to divide by the derivative of the bottom, right? If you've seen this prime notation, this just means I'm going to eventually take the derivative of it. I haven't yet. So now I could actually calculate the derivative, but instead let me just show you a shortcut. I know that the derivative of 1 plus 3 over x squared is the same as the derivative of 3 over x squared. The derivative of 1 plus 3 over x squared is the same as the derivative of 3 over x squared because the derivative of 1 is just 0. And if I take the derivative of 3 over x squared, that's the same as 3 times 1 over x squared. So that's just a constant coefficient. So I could take out the 3, and I just have 3 times the derivative of 1 over x squared. Do the same thing with the bottom. This is 1/5 times 1 over x squared. So if I take the derivative of that, that's the same thing as 1/5 times the derivative of 1 over x squared. You could just calculate the derivative normally if you want to. You don't have to use a shortcut, but I like to use a shortcut because now these two will cancel out nicely. I don't have to worry about finding the derivative and simplifying that, because often students get bogged down in those details. They take the derivative, they simplify, and it takes an extra 5 minutes. So might as well just cancel them out now, and then we don't have to worry about it. So it's a nice shortcut you can use if you want to. And that typically happens when the powers are the same, right? The powers here are the same, so we could try the shortcut. If the powers were not the same, it's not going to cancel out nicely. simplify this, I have 1/5, so I flip it and multiply, which is 5 on top. I have 3 times 5 over 1 plus 3 over x squared. And now I go ahead and find the limit. I know the limit of this is 0, so I have 3 times 5. So I have ln y equals 15. I'm not done yet though, because I'm not trying to find what ln y is. I'm trying to find what y is, right? Because that's what I originally defined the limit to be. I didn't define the limit to be ln y. So what I need to do now is solve for y. So that's why I kept writing ln y on the left side over and over again, so that I don't forget to raise e to each side. I want to solve for y. And often students forget that. So just to remember that we have to solve for y, that's why I kept writing it over and over, so that I remember the end, let me solve for y. So to solve for y, again, I raise e to each side because the exponential and log function are inverses, so if I plug one into the other, the input now becomes the output. I take e to each side, so again, e to the ln y, my input is y, now that becomes my output, which is just y equals e to the 15th. Okay, so again, 1 to infinity is an indeterminate form. Eventually we have to do L'Hopital, but we cannot do L'Hopital yet until we have 0 over 0 or infinity over infinity. Remember, you must always have limit signs, because if you don't have limit signs when you do L'Hopital, then you're saying that this fraction equals this fraction, and that's not true. It's the limit of those that are equal, so make sure you have your limit signs. So if I try inspection on the next one, I have 1 over ln 1. Well, ln 1 is 0, so I have 1 over 0. As I mentioned before, that means we would use plug-in rule, and the limit would be either positive or negative infinity. In this case, it would happen to be positive infinity, because I'm coming towards 1 from the right side, so it's going to be positive. So I have infinity, and then here, I have 1 over 0 again, which means I do plug-in rule again. If I'm going towards 1 from the right side, then as x is slightly larger than 1, this is going to be positive. So it's infinity minus infinity, which is another indeterminate form. Okay, infinity minus infinity is not 0, so be careful there. We don't know which fraction is growing towards infinity at a faster rate. So infinity minus infinity does not cancel out, right? We don't have 0 here. We could possibly have some other limit value. So what we have to do here, again, is anytime we have an indeterminate form, we're eventually going to do L'Hopital. So I know I have to do L'Hopital here, which means I have to either have 0 over 0 or infinity over infinity, which means I need a fraction. So I have a fraction here, but the problem is that I also have a difference. I have infinity minus infinity. So what I have to do is combine the fractions into 1, and then I'll have one fraction, and hopefully it's either 0 over 0 or infinity over infinity. And if it's not, then I probably made a careless error somewhere. So let's go ahead and combine the fractions. What we could do is find a common denominator and then combine. So in the first fraction, I can multiply the top and bottom by x minus 1 over x minus 1. The second fraction, I multiply ln x over ln x. Now that I have the same denominator, I can combine it into one fraction. I have x minus 1 minus ln x all over ln x times x minus 1. Now when I try inspection, I have 1 minus 1 is 0, minus ln 1, which is also 0, and the bottom is ln 1, which is also 0. So I have 0 over 0, which is exactly what I'm looking for, because if I have 0 over 0, that means I could go ahead and apply L'Hopital. So after every step, if there's time, it's a good idea to check the form before moving forward, because again, if you have an indeterminate form and you manipulate it somehow, you should still have an indeterminate form. If you don't, you probably made an error somewhere, so then you know you could go back and check your work. Now that I have 0 over 0, let's go ahead and do L'Hopital. I take the derivative of the numerator, which is 1 minus 0 minus 1 over x. The derivative of the denominator, remember to do product rule. And again, remember with L'Hopital, we're not doing quotient rule, so be careful there. We're just taking the derivative of the top divided by the derivative of the bottom. So the derivative of the bottom, we do product rule. I have ln x times the derivative of x minus 1, which is just 1, plus x minus 1 times the derivative of ln x. So x minus 1 times 1 over x. Again, if I have double fractions, we hate double fractions. We want to get rid of them. So to get rid of double fractions, what I could do is I could multiply by everything by x to get rid of that denominator. So I'm going to multiply the top and bottom by x to get rid of that x in the denominator inside the numerator and inside that denominator. So if I multiply the top by x, I get x minus 1, right? I have x minus x over x, which is 1. And then the bottom becomes x ln x plus x minus 1 times 1 over x times x, so those just cancel. Now if I try inspection again, I get 0 over 0, so I go ahead and apply L'Hopital again. I take the derivative of the top, which is 1. I take the derivative of the bottom, I have to do product rule again. X times 1 over x plus ln x times 1, that's by product rule, and then I add the derivative of x minus 1, which is just plus 1. That simplifies, x times 1 over x simplifies to 1, so in the bottom I'm left with ln x plus 2. Again, remember, every time you do L'Hopital, make sure you have limit signs. If you don't have limit signs, this equality is not going to be true, right? This fraction doesn't equal this one. The limit of them equal, and that's why we need limit signs when we do L'Hopital. So they're very important. It's part of the scoring of the rubric, right? You have to have the limit signs there. Now, I try inspection, I plug in ln1 is 0, and I'm left with 1/2. So now here's where you need to know your trig really well. When I think about inspection, I want to think, what does each piece approach? What is the base approach? What is the exponent approach? If I have a fraction, what is the numerator approach? What is the denominator approach? So I'm breaking it down and looking at what each piece approaches. So here, if I have sine x, as x approaches 0, sine x also approaches 0, because sine of 0 is 0. And then tangent x also approaches 0, because tan of 0 is 0. So I have 0 to the 0, which is another indeterminate form. There's 7 indeterminate forms. You should definitely know all 7, so you know when you have to do L'Hopital and when you don't. If you have any of the 7 indeterminate forms, that tells you you're eventually going to have to do L'Hopital. If you don't have one of the 7 indeterminate forms, then you know you can't do L'Hopital. So it's very important that you know your 7 indeterminate forms, otherwise you could be doing the wrong method with limits. So again, I can only do L'Hopital right away if I have 0 over 0 or infinity over infinity. And if any of the other 5 indeterminate forms, and I eventually have to do L'Hopital, but I can't do it yet, I have to manipulate the function to get it to be in a fraction form. So again, I have an exponent, so I'm going to do the same thing as the example 2 examples ago. I'm going to get that exponent to come down by taking the natural log of each side, but right now I don't have an each side because I only have one side. So I have to let y equal this limit, and then I can go ahead and take the natural log of each side. So I let y equal this limit, and now I could take the natural log of each side. Now using law of logs, I take this exponent and I bring it to the front. Now when I try inspection, I know that tan of 0 is 0. I know that sine of 0 is also 0. So I don't find ln of 0 because ln of 0 is undefined, and it doesn't mean the limit's undefined or doesn't exist. It just means that, okay, direct sub doesn't work here, so I just look at what it approaches. So if I look at what it approaches instead of directly plugging in, well, again, if the inside is approaching 0 because sine of 0 is 0, so again, if the inside is approaching 0, then I know by that natural log function, this limit's going to be negative infinity, right? But if you just graph the natural log function, you could see that again. So this is approaching negative infinity, this is approaching 0. So we have 0 times negative infinity. So again, getting closer to that indeterminate form that we want to. It's still an indeterminate form, which is great, because if I didn't have an indeterminate form anymore, I know to go back and check my work because I did something wrong. So anytime you use that law of log to bring the exponent down, you should have 0 times infinity or 0 times negative infinity, otherwise something went wrong. So now I want to convert this to a fraction, so I have to bring something to the denominator. It's probably easiest to bring down the tangent down. If I bring tangent down, then I have 1 over tangent, okay, or if I flip tangent, I get cotangent. So now if I bring this to the denominator is going to be cotangent x. Now when I try inspection, again the top is approaching negative infinity, the bottom, cotangent of 0, well, I know that tangent of 0 is 0. So if cotangent is the opposite, then I know I'm going to have 1 over 0, which I know is either infinity or negative infinity. But it doesn't matter which, because whether this is positive or negative, I'm still going to have an indeterminate form. So again, the numerator is approaching negative infinity. The bottom is either approaching positive or negative infinity. Who cares? It's still an indeterminate form. So we go ahead and now we can apply L'Hopital. Go ahead and apply L'Hopital by taking the derivative. Don't forget about chain rule. When I take the derivative of ln of sine x, I take the derivative of the inside, which is cosine x, times 1 over sine x. Then I divide by the derivative of cotangent x, which is negative cosecant squared x. Again, before I do anything else, let's go ahead and simplify. I know that cosecant squared x is the same thing as 1 over sine squared x. So if I know that cosecant squared is the same thing as 1 over sine squared, I can rewrite the denominator as such, and then I could just multiply this across, and I get cosine over sine. Now I have a fraction divided by a fraction. I could flip the denominator's fraction and multiply. And now when I flip and multiply, I get this. These signs cancel out, so I'm just left with negative sine x cosine x. So again, always simplify before trying L'Hopital again, because maybe you don't have to do L'Hopital, right? Otherwise, you might be doing L'Hopital forever. So simplify first. Now I could just do direct sub. I have negative sine 0 times cosine 0, which is 0 times 1, which is just 0. So again, I have ln y is 0. That's not my answer because I need to find what y is. That is what I define as my original limit. So I take e to each side. E to the ln y equals e to the 0. Here, y equals 1. Again, if I start with inspection and I get 0 to the 0, don't assume it's 0. Don't assume it's 1. Okay? That's an indeterminate form, which means we cannot determine the limit as is, and we have to do L'Hopital eventually to be able to determine what the limit is.